Okay, hello everyone. I hope you can hear me now. Yeah, just let me know. Okay, great. Great, I've set it up. Welcome to the DV Power series of webinar. The topic of today's webinar is going to be on-load tap changer testing using DVtest. My name is Vojko Mrdic. I'm application engineer at DV Power, responsible for transformer testing. So we'll start with the introduction of what actually DVtest is. So maybe some of you already know, but if there are somebody who doesn't know what DVtest is, we will briefly explain what we are talking about here. DVtest is a way of testing on-load tap changer. It is also called DRM, which is a short for dynamic resistance measurement, or some others call it dynamic recording measurement. It is a new method, relatively new method, not yet standardized. It's offline method, which means this method is testing offline transformer, which means transformer which is not under voltage. It is a non-intrusive, which means you don't need to open the transformer, you don't need to extract the tap changer, so anything can be done on the transformer, which is completely sealed. As I mentioned, the method is not yet standardized. It's not in the international standard, but it is already recognized by some of the world's biggest manufacturers of transformers and on-load tap changer. So how this method works? It works in the way that the DC current is injected through a winding and therefore through the on-load tap changer. And the on-load tap changer is being operated or moved through all tap positions. The test instrument and the appropriate software record the DC current values, and optionally they can also measure or record the motor current, the on-load tap changer motor current values, and the vibrations of on-load tap changer. So what we actually get with the DVtest is a graph, and you can see here on this photo an example of DVtest graph. So the red graph represents a DC current which is injected through on-load tap changer, and we also call this part a DVtest graph. The green one is on-load tap changer motor current, which is also recorded, and the blue one is the vibration of on-load tap changer. So you get a graph with up to three parameters. The most important of them is this red one, the DC current through on-load tap changer. And we will mostly focus on that one in this topic, in this presentation. But the other two, the OLTC motor current and vibrations, can also be very useful for detecting the possible issues and problems in the on-load tap changer. Now, if we zoom in this red part here on this slide, you can see four transitions. So you can see 4 drops of current on the red part of the graph. Each of those represents one transition. So the first one is transition from tap number 2 to 3, then from tap 3 to 4, and so on. So if we zoom in one of these, we get something like this. So each graph of the transition has some characteristic parts. And for example, for on-load tap changer with 2 transition resistors, there are typically 3 parts of OLTC graphs, which are here divided with vertical black lines. So the first part is the part when the first transition resistor is in the circuit. Then the middle part is the part of the transition when both transition resistors are in parallel in circuit. And the third characteristic part is where the second transition resistor is in the circuit. And we will show it here on this example of resistor type OLTC with arcing tap switch. So what we have here is two fixed or stationary contacts represented with the blue squares, and we have a simulation of arcing tap switch with the two resistors in orange and the main current carrying contact with the represented with the red here. So typical transition is that the moving contact will move. So when the moving contact starts to move, we are still on this linear part of the DVtest graph, as you can see here. So the first characteristic point, or let's say the beginning of the transition, is the moment when the main current carrying contact separates from the stationary contact. In that moment, the current starts flowing through the resistor, through the transition resistor, and this is this part. This is where we have the drop of current, which is caused by introducing the transition resistor in the circuit. So the next characteristic point is the moment when the second resistor makes to the next stationary or fixed contact. And from that moment, we have two transition resistors in parallel in the circuit. So we actually have a circulating current between these resistors. So the next characteristic point is when the first transition resistor separates from the fixed contact, and now all the current starts flowing from the second stationary contact through the second transition resistor, and that's why we again have higher drop of current. The transition ends when the main current carrying contact makes it to the stationary contact. So that is the end of the transition. And from that moment on, the current will increase and will get to the value which is proportional to the resistance of the next step position. So the current will not suddenly increase to the new value because of the inductance of the transformer, so it will take some time. That's why it is increasing with a ramp, not immediately. So this is typically what happens during the tap change operation. So on this graph, on this DVtest graph, we have two characteristic parameters. So besides those characteristic parts of the graph, we have two parameters. So those two parameters are transition time and ripple. So the transition time is actually the time which is necessary for OLTC to move from one tap to another. And that is actually the moment it's actually a time from the moment when the current starts to drop until the moment when the current starts to rise again to the new. And that is here represented with vertical black lines. So this transition time is expressed in milliseconds. It is usually in milliseconds, typically 30, 40, 50 milliseconds, can be 60, but generally if it is higher than that, then that represents a problem, probably in the mechanism of the tap changer. The second parameter that we also monitor is so-called ripple. It is actually a relative drop of DC current during the process. And we express it in the percents of starting current. And the ripple is here represented with the blue horizontal blue lines. So besides graphical representation of the DVtest, it is also possible to provide some numerical results. So some of the equipment and software will give you numerical results. You can get a transition time in milliseconds and ripple in percents. So there are algorithms built in inside the software that can calculate, that can detect these points when the transition starts and when the transition stops. And then it automatically calculates the transition times and ripples, as you can see here on this table. So sometimes it is easier to analyze results if you simply look at the transition times and just see if any of the transition is outside the expected limits. Okay, that was briefly about the method itself. So now when you know what the DVtest is, of course you will, what a lot of people ask is, why should we test it at all? Why should we bother with this test? Of course, there are some good reasons why this test should be done, although it is not prescribed by international standards. So I will here give 4 results. This is just one of the researches that you can find on the internet. There are a lot of them, and the numbers are different. So depending on what kind of research you take, these percents will be different. But what is common for all of them is that always the most the component in the transformer that is most prone to the damages is tap changer. In this case, in this research, it was 40%, but it can be more or less percents. But generally, OLTC is the most vulnerable part of the transformer, and there is a simple explanation. Tap changer is the only moving part of the moving mechanical part of the transformer. If we exclude oil, which is also being moved in the transformer, but from the mechanical parts, OLTC is the only part that is moving during the operation, and because of that, it is more prone to degradation of the material, and that's why it is very important to test the OLTC. Okay, OLTC failure, if only OLTC fails, is not so big issue. You can repair it, you can easily replace it. It doesn't cost as much as the transformer failure, but the problem is that OLTC failure can lead to complete transformer main tank failure, and it's roughly about 1 in 20 OLTC failures can lead to the complete transformer failure. And then that can represent a big problem, and of course it costs a lot. The manufacturers of OLTCs will prescribe the suggested period for maintenance, either in numbers of operation or after several years, depending on which is shorter. But one study showed that 12% of OLTCs require maintenance even before the manufacturers suggest. So, okay, it is good to follow manufacturers' suggestions, but sometimes it's good to test OLTCs even more frequent than that. And the DVtest allows testing the OLTC in a very efficient way and fast way. And last but not the least is around 1/3 of failures are caused by incorrect maintenance and bad reassembly. So even if you do maintenance, if you do the reparation, depending on how experienced people are doing it or not, that can even cause some problems. And it's always good to test, to check the OLTC even after the maintenance and after the reparation. And DVtest is just a very nice tool for checking the OLTC after the maintenance, just to make sure that everything is repaired correctly, everything is reassembled correctly. Okay, now when we know what the DVtest is and when we know why should we do it, we will speak a little more in depth about the theory of DVtest and show some typical graphs that you can obtain. Now, how to record the DVtest? There are actually two ways. You can do it in so-called step-by-step mode, and in this mode, DVtest is being recorded together with the winding resistance test. So if you remember from the beginning, we said that DVtest is injecting a DC current through the winding, through the OLTC, and recording that current when the tap changer operates. So, and of course, the winding resistance is measured in a similar way. You inject a DC current through the winding, you measure the voltage drop and the current, and then you calculate the resistance. So this means you can do winding resistance and DVtest together. So how does it work? If you're in the first tap position, you will inject a DC current, you will measure the winding resistance. When the winding resistance is measured, you keep the DC current flowing through the winding and through the tap changer. You operate the tap changer from first to second position, and during that movement, you record the DVtest graph, and you will obtain that information about transition from 1 to 2. And when in the second tap position, you again get back to measuring winding resistance, and after that, again, you measure the DVtest, and so on. That's why it's called step by step. So in the first step, you measure winding resistance, and then you record the DVtest. Then again, winding resistance, DVtest, winding resistance, DVtest. So you go step by step. Another way is so-called continuous mode. And in this mode, you can record only DVtest without winding resistance. So what does it mean? You inject a DC current through the winding and through the OLTC, start recording that current, and simply operate the tap changer quickly from first to the last tap position. So in that way, you are just recording a DVtest graph. You are not you are not measuring winding resistance. So we call it continuous because we are continuously recording DVtest. And this is a faster way to do that because you are not measuring winding resistance. You are not waiting for the stabilization of winding resistance results. So you can do it in these two ways. So you can do it together with the winding resistance. It will take the same time as it would take if you just measure the winding resistance. So without any additional time, you can, besides winding resistance test, you can get information about the on-load tap changer. Or if you want to do it quickly, you can do continuous mode, and very, very fast, in a few minutes, you can record all the transitions of the OLTC. Okay. Another thing that is very important for DVtest is recording rate, or how fast do we record the DVtest. I mentioned at the beginning of the presentation the typical transition time is 30, 40, 50 milliseconds. So it's a very, very quick and very fast process. And because of that, you need to record this DVtest with a very high sampling rate. What we at DVPower do is we record this current every 0.1 milliseconds. That means the transition, that zoomed part, if you remember, is represented by several hundreds of points on a graph. And that gives a very good resolution to analyze the graph, to see all those processes, all those characteristic points and characteristic parts on the graph. For example, if you would do it with a lower recording rate, let's say 5 milliseconds, then your typical transition graph would contain only 10 points. If it's 50 milliseconds transition. And that is enough just to detect whether there is an open circuit during the transition. But you will not be able to do nothing more than that. The resolution will simply not be good enough to detect the characteristic points and to detect timings of those characteristic parts of the graph. Now, performing a DVtest is quite simple, we've seen, but interpreting the graphs and analyzing them is a little bit more tricky. So it's similar, let's say, to SFRA measurements. So it's quite easy to do it. It's very easy to connect to the transformer and to take the graphs. But when you want to analyze the graph, then you need to have more knowledge, and you need to go more in depth in the theory. And so what you need to know when you want to interpret the DVtest graph is that each type of OLTC belongs to a group of units that operate at the same principle. And each operating principle provides different graph and requires some technique of analysis. So in short, you need to know what you are testing. There are many types of OLTCs, and you need to know which OLTC you are testing, which type is it, how does it work. So you need to know first the type of OLTC. Is it resistive type or reactive type? Mostly around the world you will find the resistive types. In USA, it's mostly reactive type of OLTC. So the graph will look totally different if you test the resistive type and if you test the reactive type. Now you need to know the particular model, because different models have different, let's say, for example, number of resistors. We will see later on. So you have models with 1 resistor, 2 resistors, 4 resistors, 6 resistors, and that all of those designs influence the DVtest graph. You need to know the type of transformer regulation, the type of OLTC regulation. Is it linear, plus, minus, coarse, fine? That also influences the overall graph. You need to know, is it vacuum type or oil current interruption LTC? Is it normal or regular LTC, or is it with the series transformers? LTCs with series transformer are not widely used, but there are some cases when they are used, and it's good to know them. So this is typical graph of OLTC that has a linear regulation. So what is characteristic here is that the current keeps dropping. It has a linear drop because of the linear transformer regulation. So it can decrease or it can increase depending on what direction you are recording, from first to the last position or from the last to the first. If it's plus minus regulation, the overall graph can be a V or inverted V shape. And if it's coarse fine regulation, then you have something like this. So up to the nominal position, you have a decrease of current, then in nominal position, you have an increase, and then again after the nominal position, you have a decrease of the current. Now I mentioned, so the number of resistors is also important. So here in the left upper part, you have a typical graph of OLTC with one resistor, and that is vacuum type OLTCs. They have one resistor. Usually they have one resistor only. In the lower left part, you have a graph with two transition resistors, and on the right part, you have a transition with four transition resistors. So you get different graphs based on the number of resistors. Okay, we continue with some guides for analyzing the results. So first thing you need to know, you need to look at is the linearity of the graph shape. Let's get back to one of these. Okay, let's get back to this one. If you can see here, the upper part of the graph is linear, is very smooth. So it has a constant increase and constant decrease of the current. But if you look at here, obviously you can see that the graph shape is not linear. So you have certain transitions where the current is not stable, is not smooth, and that represents problem. And if you further analyze, you can see that these parts marked with the red circle are actually physically the same tap, and the transitions taps marked with the green are actually the same tap. Then you need to, especially if it's a diverter switch design, you need to look at the difference between odd and even positions. So here on the left, we have an example of how does it look like when every odd or even position has a lower current, which indicates some increased resistance in one of the legs of diverter switch. On the right side, we have the same graph from the same LTC after the reparation. So this is linear regulation. Everything should be linear and smooth as it is on the right graph, but on the left part of the graph. So if you see any irregularity on every second position, then you probably have a problem in the diverter switch. So besides zooming the transition and analyzing the characteristic points during the transition, what you also need to pay attention is this, we call it linear part of the DVtest graph. So it is a part of the graph before the transition starts. That part should be linear and current should be smooth. If the current is not stable at that part, that means you have a bad contact somewhere. So if only one transition is problematic, then most probably the problem is related to the stationary contact. But if you have a problem in every transition, as it is shown in this second graph in the right below corner, then probably the problem is the moving part of the OLTC, because the chances are low that every stationary contact has the same problem. So we mentioned that transition time can be automatically calculated by the software, but of course it can be also checked manually on the graph using the cursors. So you can see here an example where in even tap position, in even transitions, the transition time was 76 milliseconds. In odd transition, it was prolonged 120 milliseconds. And this is also relates to the diverter switch problem. So when it operates in one direction, everything is good, but when it operates in the second direction, then you have a problem in the mechanism. The ripple values are also automatically calculated, but the same as for the transition time. They can be checked directly on the graph using the cursors. So we have here two examples, one of them when the transition resistor is shorted. So you can see it on the left graph. It is marked with a red circle. So instead of drop of current that we expect during the transition, we have a slight increase, which tells us there is no drop of current, which means there is no resistor in the circuit. So probably the transition resistor is shorted. On the right graph, you can see example when the resistor is opened. And you can see here after when the first resistor is in the circuit, the current drops from 22 amps to approximately 8 amps. And when the second resistor is introduced, the current drops to 0. And you have an open circuit during the tap changer, which is the most critical problem. Now, besides the upper part of the graph that should be linear, also the ripples should be linear. So you can see here on the left side, we can see an example of a good OLTC where all the ripples are almost linear. You have a linear decrease and increase in ripples. But on the right side is again the same graph from the few slides ago, where some of the ripples are higher than they should be. And they correlate to those same transitions where we have a disturbance on the static part of the graph. So probably increased resistance in those transitions. Another thing that you can do with DVtest is you can check the synchronization between phases. And this is very useful when you have a transformer that has 2 or 3 separate OLTCs. So for a very, very high voltages, 220 kV, 400 kV and above, you'll probably have a transformer with multiple OLTCs. So they are all in different mechanisms, and it is possible that the mechanisms are not adjusted properly, or they simply, by the time the mechanism loses its accuracy, and the tap changers become desynchronized more than they should be. So this is possible when using a 3-phase device. So the 3-phase device has the option to check the synchronization, and here on the left side you can see how does it look like when you have desynchronized tap changer. This is multiple transitions. When you zoom in one transition, you will see here, okay, these 3 colors represent 3 phases. So red, black, and yellow are 3 phases. And here on the right graph, you can see that the third phase, the yellow one, operates first. And after that, the red and the black phase operates. So you have certain desynchronism between these two, these 3 OLTCs. We mentioned that together with a DVtest, you can record the OLTC motor current. So it also can be useful for detecting some problems, especially problems with mechanisms in gears and stuff like that. So what you need to pay attention is you can check the magnitude, you can check the duration of the OLTC motor current. You can also check for some shape abnormalities. So in this graph here, you can see the two problematic transitions that are represented with the red circles. So you have a shape abnormalities in the motor current. So the motor current should look like in the first transition here. So you have a high inrush current, and then you have pretty stable motor current. But if in some transition motor current is not stable, that means motor needs some extra energy to deliver to the mechanism. That means mechanism has some problems. Now I'm going to show some faults that we simulated. This was almost 10 years ago. We went to Ireland in a workshop of ESBI and did some research testing. So we simulated some problems. We had an open OLTC available, so we could play with it. We could simulate some faults. We gained very valuable information about how different faults are related to DVtest graph. So we had a 5 MVA transformer with 11 tap position. And this research was done with the help of Mr. Brendan Diggin from ESBI and with the help of Dr. Raka Levy, who at that time was working for DV Power. So this is the transformer that we had. It's an open transformer, so we had a full access to the OLTC, which you can see here on the right side. So what we first do is we took a reference graph with 10 amps when everything was in good condition. Then we simulated problem with the moving selector contact by losing this bolt here, not bolt, by losing this spring on the, which is marked with a red circle. And we can see that during every transition we have a problem on the static part of the graph. So even before this moving contact leaves the stationary contact, we have disturbances, which means we have increased or unstable resistance. And in this case, unstable resistance was caused by bad contact, which is obtained by losing the spring that pushes the moving contact to the stationary contact here. After that, we returned this bolt or this spring of the moving contact to the proper state, and we simulated a problem with the stationary selector contact, which is represented here with the red circle. So we loosened this bolt on the stationary contact, so we can see that every transition is good one, except this where it is obvious that we have a faulty contact, that we have increased resistance, which caused higher drop of current even before the transition starts. Now I will show you some tips and tricks of how to perform the DV test and what test parameters to use, and because this can be very important for analysis of the DV test graph. Now, first question is whether we should record DV test in the up or down direction. So does it influence graph if we record it from first to last position or from last to first? Generally, our recommendation is to record graphs in both directions. This is because there are some faults that might not be visible if you record only in one direction. And also some graphs recorded in different directions, they can have a different look, different layout. So graphs recorded in different direction in most cases cannot be directly compared. You will still be able to get the transition time to see the characteristic points, but you will not be able to directly compare. So it's good to record graphs in both directions. If you don't do that, if you don't want to do that, if you are recording only up or down or raise or lower, depending on what words you use, it's important to be consistent. So if you recorded last time, if you recorded in the raised direction, then you should record it again in the raised direction. And this is an example of graphs obtained in different directions. So the same transformer, the same OLTC, the same transition. Blue is the up, red is the down direction. So the timings are still the same, but you cannot directly compare these two. This is the case of vacuum type OLTC that has one resistor. So still the timings are the same, but the graph. Another question is test current value. So what test current you should use for doing the DV test. So if you do it with together with winding resistance, of course you do it with the same current that you use for winding resistance. If you are recording only DV test without winding resistance, you should use at least 10 amps. This is because graphs recorded with lower currents can be very hard to analyze. So you can have a lot of noise on the graph. You may not be able to clearly see all the characteristic points on the graphs. Another benefit of using higher current is that it can burn layers of insulation on stationary contacts, so that those layers can develop as the time goes by, especially on those tap positions that are not oftenly used in the transformer life. So if you know the transformer and the tap changer, usually when it is online, it usually operates in just few taps. So all other taps are probably never used. So you can have some layers of insulation on those contacts. And that we also simulated in the island by putting a duct tape on one of the stationary contact. So first few times when we recorded, we get an open circuit because there was a duct tape and we could not establish the current. The current would drop to 0, but after a few times we used 20 amps DC, that current burned the insulation, as you can see here on this photo. So this is advantage of high currents. So high current can burn that insulation and can, because that insulation can give you a false alarm that something is wrong with the tap changer, that you have an open circuit and so on, but maybe it's just some thin layer of insulation that needs to be cleaned and everything can be good. So some people, when they do the DV test or even winding resistance, what they do is they operate the tap changer up and down through all positions several times just to clean the contacts before they do the test. So what you can do now, it's even better. You can inject a high DC current and operate the tap changer up and down several times, and then you will make sure that all those insulations are burned. And this is the graph. So you can see here these small ripples are normal transitions, and the big ripple is actually the problematic transition where the duct tape is. And you can see that every next time this ripple gets smaller and smaller, which means we get better and better contact. So again, the same rule as for the direction. It's important to be consistent. If you recorded previously with 10 amps, then use again with 10 amps. You can see here down below again the comparison. The same transformer, the same tap changer, the same transition. Red is the lower current, blue is the higher current. So you can see the timing is the same, but graph obtained with the higher current, the blue one, is easier to analyze. And another dilemma is whether you should record the DV test when the opposite windings are open or shorted. Both ways are valid, and both of them have advantages and disadvantages. So the benefit of having a shorted secondary or opposite winding, so if the tap changer is on the primary, if you short secondary winding, you will get the higher ripples. So the changes in current will be faster and more clear. So the graph, it will be easier to analyze the graph. But the disadvantage is that if you short the secondary, then if you do winding resistance on the primary side, the stabilization of the winding resistance on primary side will take much longer. So you will get a clearer graph, but you will prolong your measurement. So the ripples, we said, are higher when opposite side is shorted, which you can see here on this table. And you can also see here direct comparison of graphs when the opposite winding is shorted, that is a red graph, and when the opposite winding is open is a blue graph. So timing is the same, you still have characteristic parts of the graphs, but you cannot directly compare the graphs. That's why it's important, again, here to be consistent. So if you have a reference benchmark results with open opposite winding, then in the future do the testing with the open opposite winding. And of course, if the benchmark results are recorded with shorted opposite winding, you will do your next measurements with the shorted opposite winding, so you can directly compare them. So the most important is consistency. Be consistent, because DVtest is a fingerprint method. It's easy to analyze it when you have a benchmark results. So when you have a fingerprint graph, so just keep recording graphs with the same settings. So that means same direction, same test current, same cable setup, and then you will make your life easier when analyzing the DVtest graph. So just to conclude, so the DVtest, it proved to be a reliable method because there are many faults that can be detected. It's a non-intrusive method, so you don't have to open the tap changer. You don't have to do a lot of work. You can do it together with the winding resistance without additional time. You can test any type of OLTC. It's a fingerprint method. So you can also do OLTC motor current, you can do vibrations, and it's not a replacement method for DGA, so it's a complementary method with all those other testing methods for OLTCs. Okay, that would be it for this webinar. I hope you find it useful. If you have any questions here, you can have my email. So please feel free to write me to my email, and then I will gladly answer all your questions related to the DVtest of on-load tap changers. Yes, will the recording be shared? Yes, we will share. We'll share the recording, so I will send you the link for this webinar to your email addresses. Okay, there are a few questions that I can answer right now. So Robert asked, what is the frequency of testing OLTC? Once a year, a few times a year, monthly? Okay, so it's there is no strict rule how frequent you should test the OLTC. So people usually do it once a year, and from my experience, people usually do it together with the winding resistance. So depending on how often you measure the winding resistance on a transformer, in the same frequency you will do the DVtest. Question from Kim, USA. Shorting opposite winding, the bigger ripple, we short all three phases, yes, but do not ground them. That's right, you should not ground. You don't need to ground them. So you just need to ground one usually primary side or the side where you are measuring if it's connected in a star. So you just need to connect the neutral point of the side where the LTC is placed. And then when shorting opposite side, you don't need to ground the shorting of the opposite side. Okay, one more question. If OLTC is stuck, how we check externally? Okay, I'm not sure what do you mean when OLTC is stuck. It doesn't change positions or what? I think it's best. Okay, Mr. Habib Haidar, I think it's best if you send me an email with a more detailed description of what does it mean if OLTC is stuck, and then I can help to answer your question. Which OLTC, another question, which OLTC is better, single phase for each, three phase or combined three phase? Well, it depends on the voltage level. It's better to have one OLTC for all three phases, but on a high voltages, it's not possible because of the insulation and so on. So for high voltages, you need to have a three different OLTC. Yeah, okay, I think no more questions. Okay, one more question that I will answer now because we are running out of time for this webinar. What are the advantages of resistor OLTC from reactance OLTC? Okay, both resistor and reactive OLTCs have their own advantages and disadvantages. So the advantage of resistor OLTC, it is usually placed on when the tap changer is on the high voltage side. So the advantage of resistor OLTC is that it can withstand higher voltages. That's why it's placed on the high voltage side. The advantage of reactive OLTC is it can withstand much higher currents, and that's why the reactive OLTC is used when you have OLTC on the low voltage side of the transformer. Which is more preferable? That depends. Usually in USA, the network is designed in such a way that the regulation of the voltage in the transformer is on the low voltage side, and they use reactive type OLTCs. In the rest of the world, mostly the regulation of the voltage on the transformer is done on the high voltage side, and that's why they use a resistive type OLTCs. So there is no answer to question which is better. So both of them are good enough. That just depends on how you want to regulate the voltage on the transformer from high voltage side or from low voltage side. Okay, we just ran out of time, so I tried to answer as many of your questions as it was possible. Again, if you still have any further questions, please feel free to write me to my email, and I will be glad to answer them. And of course, I will send you the presentation recording by email. Thank you again for your time, and hope to see you again soon on one of our other webinars. Thank you.